So I will start recording now the meeting. And first of all, let me welcome Erin Kara to our weekly or bi-weekly now astrophysics colloquia at the University of Athens. And let me say a few words about Erin and her career. So Erin finished her undergraduate studies in 2011 at Barnard College in New York City, where she was actually introduced to scientific research, and she was mentored by Professor Resmi Mukherjee. After finishing her undergraduate studies, she was awarded the prestigious Gates Cambridge Scholarship and to get a master's degree in physics and astronomy. And later on, she earned her PhD from the Institute of Astronomy at the University of Cambridge in 2015 under the advisement of Professor Andy Fabian. After that, she was named a NASA Hubble postdoctoral fellow, and she decided to work at the University of Maryland and NASA's Goddard Space Flight Center. In 2018, she became also the Niels Gerels Prize postdoctoral fellow at the University of Maryland. And in 2019, only for 4 years after her PhD, she joined the faculty of MIT as an assistant professor of physics. So she's mainly interested in learning how the black holes in our universe grow and how they affect their environments. And she has also advanced a new technique, which is called X-ray reverberation mapping. And we are going to hear more about that today. So this technique, very roughly, broadly speaking, allows astronomers to map the gas falling onto the black holes and measure the effects of strongly curved space-time close to the event horizon of the black hole. But besides that, she has also worked on a variety of other transient astrophysical phenomena, such as tidal disruption events, galactic black hole outbursts, and ultraluminous X-ray sources. She is a NASA participating scientist for the NICER Observatory, and she co-chairs the Supermassive Black Hole Working Group, while she is also actively involved in X-ray concept missions like the STROBE-X mission and the Advanced X-ray Imaging Satellite, or for short, AXIS. So before giving the floor to Erin, I would like to say that learning about her academic journey and also being a member of the same generation, it is very exciting to watch young women like us succeed in science and astrophysics, and more importantly, become role models for the next generation of female STEM students. So Erin, thank you very much for accepting our invitation, and you have the floor.
All right, thank you, Maria. Thank you for that very nice introduction. It's an honor to be here, and I wish that I could be in Athens with you right now, but I'm happy that we at least have the opportunity to have this remote discussion. So I was asked to tell you a little bit about reverberation mapping, specifically for black hole X-ray binaries. And as Maria mentioned, I work a lot on AGN and other kind of transients. But today, the focus of today's talk will be on what we've been doing in the past, just really a couple of years, past 2 or so years on reverberation mapping in X-ray binaries. So just as a means of motivation, why do we care about studying black hole accretion flows in the first place? Well, this I think can be very well motivated by looking at how the correlation between supermassive black holes that sit at the centers of all galaxies, or at least all massive galaxies, we think. And this correlates very well with the velocity dispersion of the bulge of the galaxy. And this is the famous M sigma relationship. So roughly speaking, the mass of the black hole correlates with the mass of the galaxy. And this is kind of an amazing correlation if you think that the sphere of, or if you realize that the sphere of influence of this black hole is puny compared to the sphere, the entire potential well of the galaxy. And so why should the galaxy know anything about this little tiny black hole at the center? But what's key is that we know that black holes grow through accretion, and this accretion onto the black hole releases enormous amounts of energy in the form of radiation, in the form of relativistic outflows and relativistic jets. And this can basically affect larger scales in the galaxy, and we call this process AGN feedback. So understanding how black holes grow through accretion and how they affect their environments through these outflows, through the radiation that we see. This is like one of the biggest questions in extragalactic astrophysics. So the key, my interest in this question of how do black holes affect galaxy evolution, I want to understand like how is that energy released, in that accretion power released in the first place. And most of that accretion power is released in the innermost regions within like 20 gravitational radii of the black hole, or even smaller if that black hole is rapidly rotating. And so what we want to do is to understand how do black holes look, what do black holes look like in this very close environments, closest to the event horizon. And so we all have seen now this beautiful image of from the Event Horizon Telescope collaboration of the supermassive black hole in M87. And this was an amazing technological feat to image this, this region very, very close to the black hole. But that's only one example. And in this case, this is a very low accretion rate object. Most of the AGN that all of the supermassive black holes that are accreting at an appreciable rate, we cannot image these regions directly because the emission is not optically, this is not an optically thin region when you have high accretion rates. And so what we actually observe with our telescopes is something like this. This is hopefully you can see my pointer, tell me if not. This is an X-ray image of a supermassive black hole. We see copious amounts of X-ray emission, but we cannot resolve these regions directly. And so what we're trying to do is, using the data from this point source where we only have information on the energy of those photons from around the black hole and the arrival time of those photons at our telescope. From those two parameters, can we reconstruct what we think it must look like in these very compact environments? And so that's what today's talk is about, is using what we call these reverberation light echoes to reconstruct the inner accretion flow around black holes, to understand how is matter flowing in through this disk, how is the energy being released. So before we get into any of the details, let's just talk about this inner accretion flow. This is an artist's representation of a black hole with an accretion disk around it. If you were to turn off all of the fun, special, and general relativistic effects close to that black hole. And what you see is that an accretion disk will form around the black hole, and just due to viscous heating of that accretion disk, it becomes extremely hot and radiates thermal radiation. In AGN, this is seen in the UV peaks in the extreme ultraviolet. Excuse me for my slack. Let's see if I can turn that off. Yeah, okay. In AGN, this thermal emission peaks in the extreme UV. And in X-ray binaries, these disks get hot enough to emit in soft X-rays. But we also see, not only do we see disk emission, we also see hard X-ray emission out to 100 keV. And this is, the accretion disks do not get hot enough to produce thermal radiation out to those high energies. Instead, some of those thermal seed photons from the disk will get inverse Compton upscattered by mildly relativistic electrons in this plasma close to the black hole that we call the X-ray corona. And that process of inverse Compton upscattering those thermal seed photons will boost those photons to high energy X-rays. And so high energy X-rays are nearly ubiquitous in accreting black hole systems. What is this relativistic plasma close to the black hole? What is this corona? There are lots of different debates that I'll be telling you a little bit about today. Is it something that's more like a hot inner flow, more spherical geometry of this corona? Is it related to the base of a relativistic jet? These are things that we are trying to understand by probing the geometry and the dynamics of this corona, and how this connects to perhaps the large scale jet that we see that can reach out very far. These are all questions that we're trying to answer. So yeah, the big questions that I think that I'm interested in probing is, how is this accretion power dissipated? How do we launch relativistic jets and wide angle outflows? How do we produce the emission that we see? Next, how does matter behave in the strongly curved space-time? If you want to use black holes, accreting black holes as a test of general relativity, if that's your aim, then you better understand how baryonic matter behaves in the strongly curved space-time closest to the event horizon. It's only then, once you have a really good understanding of that accretion physics, or are you going to be able to, really probe the GR, probe gravity in that way. And then finally, how do black holes form and grow? And in particular, can we use the spin of the black hole, how fast the black hole is rotating, to inform something about the growth history? And I'll talk a little bit more about that in this talk. All right, so I think I kind of motivated that we're interested in studying these accreting black holes because at least for me, I'm very interested in the role of black holes in understanding the evolution of galaxies. But these supermassive black holes evolve. The duty cycle of these black holes is 10 to the 7, 10 to the 8 years, something very long. And it's really hard to understand this causal connection between material flowing in and energy being released and producing these jets. And so X-ray binaries, sometimes they're coined microquasars, can be a nice analog to these accreting supermassive black holes that we see at the centers of galaxies. So black holes, stellar mass black holes that are in a binary system with a normal star, can accrete material off of that companion star, and at some point in their evolution, you will see some kind of accretion episode and these sources become some of the brightest objects in the X-ray sky. So these are 4 examples of recent outbursts observed detected by the MAXI. It's an all-sky X-ray monitor on the International Space Station. And in particular, I'll be telling you a lot about this top one, MAXI J1820, from that went into outburst in 2018. And was a really exceptional source. I think every X-ray telescope observed this object, plus many multi-wavelength campaigns. So these stellar mass black holes that go into outburst, they are bright for several months, perhaps, and then they fade. And perhaps that is equivalent to the duty cycle of an AGN, just on timescales that humans can probe. So these X-ray binaries are known to show some very interesting phenomenology. I hope that you can see my slides at the bottom there. But yes, so The basic phenomenology of these X-ray binaries in outbursts can be characterized by this hardness intensity diagram that you see on the bottom left here. I should say a lot of these plots that I'll be showing come from a recent review that we just finished and is in press. So take, look out for this review in the next couple of months. So black holes that go into outburst follow this characteristic, evolution in this hardness intensity space. As they emerge from quiescence, they have, this is the spectral hardness on the x-axis and the count rate, the luminosity on the y-axis. As they emerge from quiescence, they have a very hard spectrum, kind of like what you see for, this is the case of Maxi J 1820. What you see here is they start with a very hard X-ray spectrum. And as they evolve over several weeks, they will transition. Suddenly they become very bright. They transition to a thermal dominated state. And so they start with this dominated by the coronal emission from these in high energy X-rays, and then they transition to this thermal dominated soft state after several weeks, and back to, as the luminosity decreases again, will transition back into the hard state and back into quiescence. Now, it should be stated that the basic geometry, I don't know if you're also seeing the view that I see, but the basic geometry that we kind of agree upon in this field is that as the source is in this very low luminosity state at the beginning of an outburst, you don't have enough mass accretion rate to have a radiatively efficient accretion flow. You'll have some kind of advection dominated accretion flow and a truncated disk in the very low luminosity regime. And this, hot inner flow is what you will see as this hard X-ray emission. Also, what's generally agreed upon is that as the source transitions to this soft state, then you have an accretion disk that extends all the way to the innermost stable circular orbit, and the corona becomes much weaker, and the disk is this radiatively efficient thin disk. But how this transition happens, how you go from these very different accretion states, and namely what happens when you're in this high accretion rate regime, but before the state transition to the soft state, and what happens in this this intermediate state is not well understood and is still debated in the field. Just to drive this point home, that perhaps that X-ray binaries, they're interesting, of course, on their own right, but they're also interesting because they may be analogous to AGN. This is kind of maybe a controversial plot, and I would say by no means definitive, but perhaps you could map these different states in a black hole outburst to different populations of AGN. So low luminosity AGN at the bottom here, perhaps Bal quasars or narrow line Seyfert ones in the soft state, and radio loud and radio quiet, perhaps. TBD, but it's an interesting possibility, and I think there are lots of similarities that we're seeing between some of these local Seyfert galaxies and the X-ray binaries that we're probing. The last thing that I want to mention about these the phenomenology in these outbursts is that in addition to very distinct characteristics in the X-ray band, the outburst also shows multi-wavelength emission, and in particular, what you see in the hard state is that as this source emerges from quiescence, you see this brightening of a synchrotron emission in the radio band. You see a compact radio source, a persistent jet. And then as the source evolves to the soft state, you see this persistent jet begin to decline. And at some point, what we call the soft intermediate state, or around this region, you see often a transient ballistic jet. And you can even see in several cases that you can measure, kind of relativistic ejecta blobs moving out and you can even measure superluminal motion in some cases. And you can track resolve these with VLBI, these jet ejection events. And then after this jet ejection event, the source transitions to the soft state, this thermal dominated state, and you do not observe any jet in this thermal dominated state. In fact, you only see kind of equatorial winds in the soft state. So clearly there is this kind of hysteresis effect happening also with the jet emission that we observe. And the big connection is the big question is, how exactly is the disk and the corona and the jet coupled? So what we want to be able to measure now and probe more is exactly what's happening in this, how does this transition actually take place? Okay, we've agreed on the low hard state, the low accretion rate state. We've agreed on that the thin disk extends to the ISCO in the soft state, but how do you actually make this transition? And what's happening, what's the geometry of the accretion flow in this luminous hard state and during the state transition itself? And there are kind of like two general pictures. I think there's lots of kind of differences. There are more than two models, but I'll just, for the sake of simplicity, kind of say that break it down into two general models. One where you have you continue the hard state means that you have a truncated accretion disk. And the hard emission that you see is from this hot inner flow, this advection-dominated accretion flow. And as you increase in luminosity or accretion rate, this radiatively efficient thin disk moves inwards, and the hot inner flow is kind of quenched. So this is what we will refer to as the truncated disk or hot inner flow model. And then the other is that and several on this call have worked on models related to this, is that you have a corona that the corona is the base of a relativistic jet. And in this case, the corona is something that is more vertically extended. And then, how you explain the evolution in this in the state transition is not really that the disk needs to change very much, but rather that you're seeing more evolution in the geometry of the corona. And so there are kind of different permutations on this model, but we'll say that for the sake of just these are two general models. One that most of the changes in the truncation radius of the disk, and the other that you're really seeing an evolution in the corona in the state transition. So now, how do we get at answering this question? The technique that I'll be telling you about today is X-ray reverberation mapping. And the idea here, don't really pay too much attention right now on the geometry of this corona, but really this is just a schematic that the NASA press office put together for me. That's showing, this is a cross-section of an accretion disk. This is the accretion disk here in cross-section. And this blue bit that's radiating here is this X-ray corona, this hot plasma, relativistic plasma producing the hard X-ray emission. This corona will emit more or less isotropically in its rest frame. And some of those photons will come to us directly, producing the hard X-ray continuum that we observe. And some of those photons will irradiate the inner accretion disk. And what we can do is measure those, the response of the accretion disk to that irradiation from the corona. And there should be, light travel time delays that help you map out both the geometry of the corona and the inner accretion disk here. So what is it that we're actually seeing as this corona irradiates the accretion disk? Some of those photons will be scattered off of the accretion disk, Compton scattered off of the accretion disk, producing this Compton hump that we see at high energies. Some of those photons will be photoelectrically absorbed and fluoresce and produce emission lines like the iron K alpha line and a plethora of other emission lines at lower energies. And some of those photons that don't cause fluorescence or don't get scattered will heat up the accretion disk and cause thermal reprocessing as well. So lots of different effects happening, and we call all of this together the reflection spectrum. It's not an actual reflection, but it's the reprocessed emission off of the accretion disk from this corona heating, irradiating the disk. So in addition to we see these emission lines, but we can also use not just what lines that we're seeing, but the broadening of those lines to tell us something about as a diagnostic of the geometry of the accretion disk. And so that is because basically you have this, this accretion disk is not a static slab of gas, but rather it's a rotating system. So you're going to get Doppler effects, broadening that line. You're also close to a black hole. So the emission coming from the innermost regions will be gravitationally redshifted as those photons escape the potential well of the black hole. Adding up all of those effects, produces this asymmetrically broadened iron line that you see. So we have the Doppler shift, we see some special relativistic beaming of the emission from the side of the disk that's approaching you. General relativistic effects are going to shift all of those photons to lower energies due to the gravitational redshift. Add up all those effects, you get this asymmetrically broadened iron line profile. All of this iron line profile and all of these reflection features should be delayed with respect to the continuum emission due to that extra light travel time delay that those reflected photons have taken. So because we can measure the effects of the gravitational redshift, we have the opportunity to measure the inner edge of the accretion disk. And you could imagine that photons that are coming from a truncated disk or a disk that's further out, you won't see as strong a gravitational redshift as in the case of an accretion disk that is not truncated and rapidly rotating. You'll see that accretion disk extends to 1 GM over c squared, 1 gravitational radius. And so you're going to see maximum gravitational redshift and a very strong broadening, red wing due to the strong gravitational redshift. And so we can use this broad iron line to measure the inner edge of the accretion disk. And if that inner edge of the accretion disk is at the innermost stable circular orbit, then we can use that inner edge, that measurement of the inner edge of the accretion disk to estimate the spin of the black hole. And that is because the ISCO is determined by how rapidly rotating your black hole is. So if you have a prograde rotation, frame dragging, general relativistic frame dragging effects are going to support more orbits closer to the black hole, and that ISCO moves inwards. And in this case, you'll have a stronger gravitational redshift of that iron line. And so this is important because measuring the spin of the black hole is, not only is the spin like one of these fundamental parameters of the black hole, but it also greatly affects the radiative efficiency of this black hole, basically how much luminosity you can get out for the mass accretion that you're, shoving into the black hole. But not only that, the spin of the black hole can tell you something about how that black hole grew. So for stellar mass black holes, it'll tell you something about the interaction with the companion. As material accretes onto the black hole, it will spin up over time. And in AGN systems, this may be a way of getting us to understand how did these supermassive black holes form? Did they mostly form from prolonged accretion? As material accretes onto this black hole, it'll spin it up over time. Or did these black holes mostly grow from mergers, where you should have two black holes that are merging that don't have a preferential spin axis, and you would expect to see a different distribution of black hole spins if you were to measure these in a large sample. So this is one of the reasons that we're interested in measuring the spin of the black hole. And we can talk more. There's other reasons as well we can talk more about. But this broad iron line is one of our best ways at estimating the spin of these accreting black holes. So let's get back to this idea of measuring these light echoes. What is it that we're actually doing? These reverberation light echoes, the time delays between that continuum coronal emission and the reflected emission off of the accretion disk, these are first measured in AGN systems. And this is the example of 1H0707, the source where it was discovered. What we do in this technique is we take an energy band that is dominated by the reflection. In this case, this is a spectrum where we've divided out the continuum. And what you see is the iron K, the broadened iron K emission line at 6.4, and the iron L emission line at lower energies here. We take a band that's dominated by the reflection and measure the time delays with respect to a band that's dominated by the continuum. And in the reverberation picture, you should see this reflected band lagging behind the continuum band. And in practice, what we do is that we need to look at this in a Fourier resolved approach, because we see accreting black holes vary have a red noise power spectrum. They vary on lots of different time scales. And in particular, we see time delays associated with different processes that dominate on different time scales. And so what we do is we use this Fourier resolved approach so that we can isolate just the most rapid variability. And that's presumably coming from the innermost regions. And what we observe is that if you can isolate those highest frequencies, that most rapid variability, you see this negative lag here. And negative in the canonical definition or the conventional definition, negative lag means that the soft band, this reflection dominated band, is lagging behind the continuum. And this is this signature of reverberation light echo. So it was very exciting when people saw this for the very first time. This is a 30-second lag, roughly, in a 10 to the 6 solar mass black hole. If this, if you did the naive thing of just directly converting 30 seconds into GM over C, into a light travel distance in GM over C squared, it corresponds to like 2 gravitational radii from the black hole. So this was, we've seen AGN reverberation lags in a number of systems now, and this is just to emphasize that on long time scales, what you observe is lags that are not associated with reverberation, and this is why we need to use this Fourier resolved approach to kind of get rid of those lags, or not focus on those lags. And these lags on long time scales are kind of featureless in how they evolve with energy. And this is because they're thought to be associated with the continuum itself, perhaps mass accretion rate fluctuations that kind of propagate through the accretion disk and produce this featureless spectrum. And if we can isolate the lags just associated with the highest frequencies, then we see signatures like the lag of the iron K band and some of these other reflection features at lower energies as well. This is this high frequency soft lag, this signature of reverberation. So we've been able to do this now in a number of AGN, and what's cool is that the amplitude of the lag scales with the mass of the black hole for a sample of AGN. And this is kind of what you would expect if what we're probing is the light travel time between this accretion disk, this compact corona at 10 gravitational radii or something, and the accretion disk. So now let's move on to X-ray binaries. X-ray binaries, they are 1,000 times brighter than AGN. And so you might think, okay, they're the perfect system. Why wouldn't you do this in X-ray binaries from the very beginning? Well, they're 1,000 times brighter, but their time scale of variability is like 10 to the 5, 10 to the 6 times faster than AGN. So the number of photons per characteristic light crossing time is a lot less in X-ray binary systems. And so this in some ways makes it a more difficult problem in X-ray binaries. Thankfully, we have really huge telescopes like the NICER Observatory now, big effective area telescopes that are allowing us to probe now reverberation lags in X-ray binaries as well. So these were first discovered by Phil Utley in 2011, and some really awesome follow-up work by Barbara DeMarco, probing the evolution of the reverberation lags during a state transition. And I'm going to now focus on newest results with the NICER Observatory of the very bright outburst of Maxi J 1820. So Maxi J 1820 was an outburst of a low mass X-ray binary in March of 2018. Maxi found this source. Maxi, this all-sky monitor on the International Space Station, found it and announced this with the observation. NICER is also on the International Space Station and slewed very quickly to observe it, and basically observed it every day during its outburst. And this is just the evolution of that light curve over time. And what you're seeing just color-coded in time on the left. And what you're seeing is the same color coding in time, but now projecting the hardness intensity. So you can see how it begins in the hard state, this low luminosity hard state, and evolves to the soft state and then back again. So we're going to focus on that pivotal region that we were saying, where it's debated how this source evolves. Is the accretion disk truncated in the luminous hard state, or is the disk not truncated, and instead what you're seeing is mostly an evolution in the geometry of the corona. So what was nice was that we were able to study these lags as a function of temporal frequency. Now, we're looking at X-ray binaries, so we're looking at much more rapid, much higher temporal frequencies than in the AGN, of course, and much shorter amplitude lags, but still the same. You see when you take the lag between the soft and the hard band, what we observe of a reflection-dominated band and a continuum-dominated band, we see this negative lag at high Fourier frequencies. This is this signature of reverberation light echoes. So even in this first observation, we were pretty excited because this was a shorter lags than we had previously been able to measure. But as we watched the source evolve over several weeks, we saw that the lags got shorter and shorter, probing higher and higher frequencies. So the lags evolving to, becoming shorter was telling us something about the size of the emitting region getting smaller. And this in and of itself could either be due to the truncation radius moving inwards as you increase that mass accretion rate, or could be driven by the corona contracting, a vertically extended corona that's contracting over time. And from the lags alone, you can't really distinguish between these two possibilities, but they both, what the lags are showing is that the emitting region, something in the emitting region is getting more compact as we watch this source evolve. But what's really nice about NICER is that in addition to having, being able to measure these time lags, it also has very good energy resolution. And so you can measure this iron line profile over these same epochs. And what was very cool was that there's kind of a broad component and a narrow component at the rest frame energy at 6.4 keV rest frame. And what we noticed was that the broad component of the emission line, this gravitationally redshifted bit of the line, did not change at all, even though the lags were telling us that the emission region was getting smaller in the system. The gravitational redshift wasn't changing very much. And so this suggested to us that, it wasn't that the inner accretion disk was moving in. If the truncation radius is getting smaller, you'd expect low gravitational redshift when it's very truncated, and more gravitational redshift. You'd see a change in the shape of that iron line if the truncation radius was changing. But instead, what you see, this is more consistent with a vertically extended corona, where you have some of the corona is constantly irradiating the innermost regions, producing this constant broad iron line. But the geometry of the corona is contracting during this state. And that can explain the shortening of these lags. So what is interesting is that this contraction of the corona happens at the same time as this persistent radio jet decreasing in luminosity. So in the last couple of minutes, I want to just tell you about some of the newest work that we've been doing. This is with my graduate student, Jingyi Wang, fourth year student at MIT. She has now extended these studies not only to this luminous hard state that I showed you from my previous work, but also now to the state transition. And this was kind of a big deal because the variability drops dramatically during this state transition. And so it's traditionally been extremely difficult and not possible to measure reverberation lags during the state transition. But because of NICER, this awesome new telescope, and because we had this bright outburst, she was able to measure the reverberation lags during the state transition. And what she found was something pretty exciting, that during the state transition, in the hard state, we had watched the contraction of this corona, but during the state transition, she found something very different, that the lags didn't just keep marching to higher and higher frequencies. They didn't just continue to get shorter and shorter. Instead, they get longer during this state transition. And this was also seen in a follow-up work by Barbara DeMarco during the state transition. What Jingyi did next was she wanted to understand, what does this mean in the context of the geometry of the corona? So she used this general relativistic ray tracing simulation called RelTrans to model these time lags. This is basically saying, what are the time lags that you expect from a lamppost corona? Just for the computational ease, we use a lamppost point source corona, and shine that in all directions, some of those photons will hit the accretion disk and cause this reverberation light echo that we can then use this model and apply it to the data to kind of estimate both the location of the corona, the inclination of the disk, etc. And what Jingyi found was that during the state transition, during the hard state, as we saw before, the lags get shorter and shorter. This can be modeled as a decrease in the height of the corona. And then suddenly during the state transition, the height of the corona expands. And so perhaps this is related to the interesting, there's this ballistic radio jet that is produced right before the, at the very ends of the hard state, right before it enters the soft state, there is a ballistic radio ejection event. And what was interesting is that this measured expansion of the corona from the longer reverberation lags precedes this strong ballistic radio flare by 5 days. And so perhaps what we're seeing in this system is that, the corona, if it's related to the base of the jet, perhaps this is like the launching point of the jet. And what we're seeing is the initial acceleration of this, some kind of ejection event that you see days later in synchrotron emission in the radio band at like 10 to the 7 gravitational radii. And so this is perhaps a tantalizing suggestion that this extent of the corona is really probing the acceleration region of the jet. And so this is kind of the general picture, putting this all together, that in the hard state, as we kind of get to the end of this luminous hard state, this persistent jet begins to quench just at the same time as the corona contracting. And then during the state transition, as right before this ballistic jet is observed in the radio, we see an expansion of the corona, perhaps suggesting that there is this disk corona and jet connection. So what about, is this just Maxi J 1820? Is it just this very exceptional bright source? Jingyi has continued now. This is looking at several sources in the NICER archive. And what she's discovered is that this is not just a special event in Maxi J 1820, but instead reverberation lags can be measured in several low mass X-ray binaries. And what she observes, this is a little bit of a complicated plot, and I won't even go into describing what this hue is, but suffice it to say that it is an indicator based on the variability amplitude of the light curves of the power spectrum. It's a way of disentangling or kind of classifying what state a source is in, what accretion state the source is in. And basically what she found was that a source evolves from the hard state into the hard intermediate state, and then finally into the soft intermediate state. During this transition, during that state transition, the reverberation lags get longer, not just in J1820, but in a number of sources. So this seems to be a consistent disk corona jet picture that the corona expands, during this, before the ballistic radio jet is observed. So that's all that I really wanted to get through. I think I'm doing okay for time. And I hope you've learned a little bit about this reverberation mapping technique and implications for probing the disk corona jet geometry in X-ray binaries. Thank you.
Thank you very much, Erin. This was a very exciting talk and informative. And I think that we will have questions. So let me So if you have questions, first of all, you can raise your hands, or if you cannot speak for any reason, you can also type them in the chat and I can ask Erin. And I see one hand raised by Nick Kilafis, so please go ahead.
You're muted.
I think he's muted. Okay, ask to unmute.
Sorry. Yes, I'll repeat. I said, Erin, this was an excellent talk, thorough for the subject and yet educational for the young people. Thank you very much. This was excellent. I wanted to ask a question. If you could show one of your slides that contains the curves that you plotted in your Nature paper, your 19 Nature paper. It's towards the end. Before that, right, that. Now, these curves have both positive and negative lags. And you discussed the negative lags. Do you want to say anything about the positive?
Well, I know from your work.
Yeah, but I do not want you to mention my work. I'll tell you what I see here. I see in the red line, I have the maximum negative lag. And I have positive lags at at low frequencies.
Yes.
Then, as the colors change, I see positive lags at higher frequencies and smaller negative lags. So, and it's always a continuous curve as you have plotted it. So it looks to me that it is the positive lags that determine where they will meet with the negative. Imagine a master curve negative, and then add all these positives. And so the intersection of the two will move to higher frequencies. Could one interpret it like that? I do not know how to interpret it, but I'm just asking.
Yeah, so I think that it's a really good point that, you know, the most obvious thing that you perhaps notice is that this evolution of both of the hard lag as well. And I do think that that is important and needs to be modeled together with the reverberation signature. What I'll say is that, so you could interpret it as just, you know, perhaps just due to a change in the hard lag. What I will say though is that this frequency at which the soft lag goes to 0, that's really very strongly constrained on the finite size of your emitting region, your reverberation, you know, the size of your reverberation region. And the fact that we also see this frequency also evolve in frequency, perhaps less clearly, and with more scatter. Of course, you're at like high frequencies, so it's harder to measure these lags. That does suggest that it's not just, you know, this isn't just an evolution in the hard lag alone, but you're also seeing a change in the size of the reverberation echo region.
If I may ask one more question, and then I'll shut up. How big is your corona? Do you quantify the size of your corona? Where I'm leading is the following. You may have your favorite mechanism for the positive lags. However, you have Comptonization in the corona to get the hard X-ray spectrum. Yes. So, and Comptonization produces hard lags, and only if the corona is small, one can neglect these Comptonization lags.
Correct.
So how small do you quantify in your models the size of the corona? Because that will determine then whether Comptonization lags are important or not.
Yes. Yeah. So I'll say this is, I think that there's really compelling evidence with the broad iron lines, right? That like you need to have some bit of the corona that extends close to the black hole, that is compact, that isn't very radially extended, or else, you wouldn't have seen such prominent broad, gravitational redshift. The vertical extent is something that I think that we're working on. I would say there has been spectral modeling of these data that suggests that what you're seeing is at the beginning time something like 30 gravitational radii extended, and then as it contracts down to like 10 gravitational radii or so. In which case, these Comptonization lags, I think, would not be that important, or couldn't totally be explained, couldn't explain the long hard lags that you see if you have such a compact corona. During the transition, we're seeing the lags increase by like almost a factor of 10. So then that, if you model those time lags, you get if it's 10 times bigger, then it suggests a coronal geometry of like 100 RG. So in the transition, I should also say though, in the state transition, you're not really seeing much hard lag anymore, but that may be because of the times we're not probing long enough timescales.
Okay, thank you very much.
Okay, I see another hand raised by Apostolos Mastichiadis.
Yeah, hi.
Hello.
Thank you very much, Erin, for your talk. I learned very many things. I'm not like my friend Nick in this field, but a little bit outside. But so I have a more naive question. Talking about your spectrum formation. First of all, what causes your corona to come up and down? Because you talked about extending the corona or contracting it, and very fast, if I understand correctly. Is there any physical reason why you want this? I mean, okay, maybe it comes from observations or future data, but why you would expect something to vary so quickly?
Yeah,
that's
it's an excellent question, and I would say that what I've told you is definitely an observationally driven result. And what heats the corona is an outstanding question. Something must be related to magnetic fields in the perhaps that. Now I'm going to be waving my hands now that I'm talking about magnetic fields, but that there are magnetic fields that are kind of threading this accretion disk. If they get twisted in the innermost regions, you can have heating due to magnetic reconnection, perhaps. And if that's like driving the corona, and perhaps as the accretion rate is changing in the hard state, that change in magnetic field structure will change the geometry of the corona.
Okay, thank you. And also another thing. Okay, I understand that you have the disk photons that are up-Comptonized in your corona, and you produce X-rays. At the same time, you have a jet.
Yeah.
The jet, and you talked about synchrotron radiation. This means that you have electrons there, which are of some energy, which is not thermal, and at the same time you have all your soft photons around. Therefore, you have straight inverse Compton on your on these electrons.
Yes.
Where is this component? Is it hidden behind your corona, or why don't you see something from this? I mean, you see what I mean? You have electrons moving out because they produce your synchrotron. You have soft photons from the disk. Therefore, you have, I guess, enough inverse Compton. which is different from the comptonization component. Therefore, what is this component?
I think that
it's hidden.
I think that there is still room that this could be a component that we see producing some of the hard X-ray emission. Yeah.
But you cannot disentangle the two.
There are some efforts, but I would modeling the high energy X-ray spectrum, and I would say that it's NuSTAR has been really important for these studies, but I think that the jury is still out.
Anyway, okay, thank you, and thank you for your excellent work.
Thank you.
Okay, are there any other questions? I also had a similar question with Apostolos, Erin, so it was related to the presence of the hot electrons in the corona that you need for the comptonization, and then in the picture that you described about the transition phase between the hard and the soft, where you have this expanding corona, and then you have the formation of this blob that you see in radio, which basically you detect it further away. So I was wondering if you could say, or if you have a number in your mind, how much is the distance between the extent of the corona and the distance where you see this radio emitting blob? Is it like, maybe you mentioned it and I missed it, hundreds of RG or even larger? Because
yeah, I mean, I would say these are all like, don't put too much into these numbers, but something like 100 RG extent of the corona, and then you see this, by the time you see it in the radio, something like 10 to the 7, 10 to the 6, 10 to the 7 gravitational radii. Okay. So if it's accelerating, at close to the, up to at velocities close to the speed of light, then you can get that in 5 days.
Okay. So one could basically, yes, even consider, that also particle acceleration takes place within that very large distance. So you might even suppress the inverse Compton emission on the soft photons from the disk if the relativistic electrons are further away. Okay. Yeah. Okay, so I see one more hand raised by George Vasilopoulos.
Oh, I can't hear you.
We cannot hear you.
You don't seem to be muted.
No, something is wrong. With the headphones, maybe.
Now, can you hear me?
Yes.
Okay, yeah, something happened with the headphones, and so thank you for the great talk and the very interesting things we learned. So I have a question about the last slides you showed, that now you have studied 4 or 5 different systems and they all seem to have similar behavior, and I'm curious, like reflection and reverberation are a very well motivated model and well structured on what we expect to see and what you can model. So I'm curious, like, what else is now there to find? Like, what, as you want to observe more systems, what is there a smoking gun to find extra signatures that you're expecting and we haven't seen yet? Do you expect some systems to behave differently? And maybe a second part question for future X-ray missions, what you would like to have in order to explore these new ideas or whatever might be for that. Thanks.
Yeah. What a lovely question. I would say what I really think that we need to understand is I think that we're making a lot of strides in on an observational front, and I want to have a better answer to the question of how is this corona heated and how does this corona evolve, and what's the mechanism behind it. So I think that there's a lot of work to be done in MHT simulations and like on a theoretical front, and connecting theory with observations and having simulations that reflect better the radiation that we see, including radiation in those simulations. So I think that that's kind of at the cutting edge. I also think that there's a lot that, I focused on X-rays and told you a little bit about also how that maybe connects to the radioluminosity, but could we actually measure like the time delays between the X-ray emission and, for instance, the infrared radiation that comes presumably also from the jet? And there's been a lot of efforts in this space and a lot of really cool stuff. Tedorenko and Vincentelli, a lot of people working on X-ray, IR, and causal connections. And I think that'll be really cool to probe. It's really hard to coordinate those campaigns because these are like, vastly different techniques. But can we, incorporate that and get those observations in the state transition, I think will be really helpful for understanding the corona jet connection. So yeah, that's what I'll say.
Oh, thank you.
So there is time for more questions also from the younger people in the audience. I would encourage them to ask questions because they are usually very shy.
Everywhere.
So I see also Nick Claffey's switched on his video. Maybe he has a comment or question.
I will not ask a question if somebody else has, but if nobody
else... I don't see at the moment any raised hands, so maybe you can take the time and...
Okay. Erin, can we go back to that same slide? There it is. Okay. You have your favorite mechanism, and not only you, the entire community has the favorite mechanism about the hard lags, that they come from propagating fluctuations. And I say, no, they come from Comptonization. So one day, one of us will be proven wrong, or both of us will be proven wrong. Who knows? But my question is, if these positive lags come from some other mechanism, not Comptonization, therefore they do not talk to the reverberation lags, which come from Comptonization. They come from scattering of photons. If the hard lags do not come from the upscattering, then how do they know where to cut off? For example, they could overwhelm the other ones and you don't see them at all. Because if the purple line is moved a bit to the right, then there is no negative lag because it's washed out. You see what I'm saying? So it's just a question for thought, not to answer now. What would happen if these positive lags were a bit to the right and completely washed out the others? Is it an accident that this does not happen? So it's a question for thought.
Yeah, I think it's a good question, and I think that that there must be some connection between. Even if your preferred interpretation is that the hard lags are intrinsically due to mass accretion rate fluctuations that propagate inwards, there obviously must be some connection to the corona. And that's like the only way that you would see these lags in hard X-rays at all. So like you can't get away from that aspect of things. And yes, I think that that's a really like important question, is to ask, like, why is it that the reverberation the hard lags are being diminished at some frequency, they disappear so that you can see the reverberation at the highest frequencies, and folding that into the model is really important. Yeah.
Yeah, I don't think it's an accident. It's telling us something. I don't know what it's telling us.
Yeah.
Because I don't have a model for these curves. Pablo and I are working on that, but we don't have anything yet. Therefore, it's a mystery to me also.
Yeah. Yeah. I think that actually the models are I like your model a lot, and I think I see a lot of I think they're converging in a lot of ways, and if we'll see what happens. I mean, obviously there will be a time delay from Comptonization, and it's just about like figuring out what is the radial extent of the corona, as you say.
Okay.
Okay. So I don't see any questions in the chat. So your talk was perfectly clear, I think, to the students of the audience. So thank you very much, Erin, and it was really exciting. And hopefully...
Time to clap our hands. Time to clap our hands.
Thank you. I appreciate all the good questions. Food for thought.
Thank you.
Thank you. And yeah, we'll be watching for papers from your group to come out and see what happens with more systems. And maybe some of the people here will have some theoretical models to propose as well.
Yes, please let me know.
Yeah, so I think here in Greece we have more like strong theory groups, so perhaps we can send some of the students there.
Sounds great. Yes.
Start running the simulations.
Please be in touch. Yeah.
Okay. Thank you very much.
Thank you.
And we will see you hopefully in the summer at COSPAR.
I hope so. Yes. Thank you for the invitation.
Thank you. Bye.